Welcome everyone. Sorry for the delay. There was some technical problem from my side. Um, so today we have Professor Shobha Madan with us from the Indian Institute of Technology, Goa. Before going into her talk, just let me mention two things. First is that please use the chat option to ask any questions that you might have for Professor Madan, and I'll put them to her either during the talk or later at the end. And if there is any technical problem, then just again use the chat box to let me know. And if I'm able, then I'll assist you. So let me introduce the speaker now. We have Professor Madan with us. So she's a distinguished visiting professor at IIT Goa. Before this, she had held positions at IIT Kanpur and IISER Mohali. And she did her PhD from IIT Kanpur in 1980. She is a distinguished harmonic analyst who has inspired generations of students by her teaching and expertise. And we are very pleased that we have Professor Madan with us today. And she's going to speak about almost arithmetic progressions in substantial subsets of integers.
All right, thank you, Manjil. I can start now, Manjil?
Yes, Professor Madan.
Okay, so I'm very happy to be here. I've been watching some of the lectures and it's been done very well and rather interesting. So let me begin. This title has things that need to be explained, but they will be explained during the talk. First is the word almost, which should have been also in inverted commas. Almost arithmetic progression, which I will explain, and what is meant by substantial will also emerge. So I will say, let me tell you the structure of my talk. It's basically two parts. The first part is like telling a storyline. It's a very dynamic storyline, and it is the work of some of the giants of mathematics in our lives. And this is not the mathematical content of this. I do not know myself, except for a little epsilon. That is, I've read one paper long time back. The rest is just the storyline. In the second part is when I will come to the almost arithmetic progressions, which is approximation or a weaker version of one of the conjectures. So where I will actually prove something. Every talk one must prove something, so I will prove something. But the major part is the storyline. Yeah, next. So I'm going to start by what is called a warming up exercise. Everybody knows all about prime numbers. And I'm not yet talking about substantial, but yes, in a way, the set of prime numbers is in some ill-defined way substantial in the sense that there are infinitely many primes. And for the sheer beauty of these proofs, there are many proofs of this. We'll talk about a few, not too many. So the first, of course, is Euclid's proof. It's fascinating that he proved this in 4th century BC. So the proof goes like this. I'm sure everybody knows it, but we go through it again for pleasure. That suppose that there are only finitely many primes. Let's say P1 to Pn, and that's it. So we construct a number n, which is a product of these primes, and add 1 to it. So in the process, n, either this n we have constructed is a prime, it may not be, but if it is a prime, then we have actually constructed a prime larger than Pn. But if n itself is not a prime, and then it has to be, by the unique factorization theorem, it has to be divisible by some prime. But the prime that it is divisible by cannot be P1 to Pn because they don't divide n. So there must be a larger prime. So that's it. That's Euclid's proof. Very neat, contrapositive. Okay, next. So the other, I'm going to do another. Yeah, thanks. This is another proof of infinitude of primes. And what it does is it constructs these numbers fn, which is 2 to the power 2 to the power n plus 1. These are called Firma numbers. And we can prove that pairwise these are co-prime. So what would that mean? If pairwise they are co-prime, then their factors keep producing primes, which are not in any other, which are not factors of any other, and these are infinitely many numbers. So you'll keep getting infinitely many primes. So you prove this by induction. Essentially, there is one thing here, that Fn can be expressed as a product of the Fk's up to n minus 1 plus 2. This is easy to prove. Now we want to prove that these Fn's are pairwise co-prime, but it's easy to see that if P is a common divisor of Fk for some k and Fn, then P will have to divide Fn minus 2. P also divides Fn, so P will have to divide 2. P will be actually 2, but 2 cannot divide the Fermat numbers because they are all odd numbers. So that's it. So this one sort of makes sure that you can construct large numbers, Fn's, and each one will certainly have some prime other than the ones constructed before. So that's another proof. I'm going to go to the last proof for this warming up exercise. Yeah, next. And this is Euler's proof. I've chosen Euler's proof because it already makes you look at something that looks like Euler's formula. But so here he says if there are finitely many primes, then we form a product of the reciprocal 1 by finitely many primes is a fixed number. Now for the right-hand side, for each factor, we take the truncated Taylor series up to some m. It doesn't matter. At the moment, later on, we'll let m become large. And then you notice that Pn will be greater than equal to the product of these truncated Taylor series. But now when you look at the product and expand it out, each term will look like
We seem to have lost Professor Madan. Just hold on for a few seconds.
I don't know why this happened.
No problem.
Okay, so I was just trying to say that when you expand, when you expand these product things in the product, then you will actually get all integers up to P1 to the power n, P2 to the power n, and Pn to the power n. But we know that summation 1 over j diverges, so that cannot happen because Pn was a fixed number. Okay, so much for the infinitude, which was really saying mildly that it's a substantial subset, the set of primes. Next slide. Okay, so there are infinitely many primes. There are infinitely many sequences of integers, but how sparse or how dense is a set of primes in the set of natural numbers? So one measure of density, which is that natural for a subset A in N, is to look at the proportion of elements of A in a set like 1 to N, and then look at this asymptotically. So for measuring this proportion, you have the cardinality of the set A intersection the set of integers 1 to capital N. You divide by n, so you get the proportion of elements of A in n elements, and then you take the limb soup. So that is called the upper asymptotic density of A. So this is one kind of measure of a set being substantial. So we will first work on this one. Next. So the first fact is that if the upper asymptotic density is strictly greater than 0, then that implies that series 1 over n, where n belongs to our subset, diverges. Let me say this, that summation 1 over n diverges means that there are sufficiently many n's in A that contribute to the terms of this. For example, I mean, if you take something like 1 over n square, rather terms n square, then that density is, that anyway, the density, they're not enough terms. So upper asymptotic density being greater than 0 implies divergence. This is not a difficult proof, so we'll just go through it. Suppose this delta A is strictly positive. Then we are going to choose iteratively, inductively, a sequence of numbers, capital N, K. We start with 1, and then we choose Nk large enough from the choice of Nk minus 1 to be greater than 4 Nk minus 1 by delta. And we are choosing it large enough by the density criteria, density is delta, so that A intersection, the interval 1 to Nk, is greater than delta by 2 Nk. Because once you divide by Nk both sides, then you are getting the proportion. So you just write the sum, summation 1 by n in A, and you do this in blocks, Nk minus 1 Nk. So you start from N0, go up to N1, go from N1 to go N2, and then you sum up all these blocks, all that you find in these blocks, A intersection Nk minus 1 Nk. So that will be greater than equal to the cardinality of the set inside in the second sum minus Nk minus 1 divided by 1 over Nk. That is because in that interval 1 over small n will be greater than 1 over Nk. And then you just put in the way, substitute the way Nks have been chosen, and you get that this will be greater than equal to delta by 4 for each term. That tends to infinity. So it's a pretty standard argument, but the density greater than 0 will mean that summation 1 by n for n belonging to our subset diverges. Next. Of course, the converse of this result is not true, because as an example is a set of primes, because in 1737, already using his the Euler formula, he had proved that summation 1 by p is infinity. So this is a series that indeed diverges, but it has density 0 by the prime number theorem, because pi n goes as n by log n. So pi n by n. Pi n simply counts the number of primes less than equal to n. So that divided by n goes as 1 by log n. So that will tend to 0. So primes have density 0, but summation 1 by p diverges. Yeah, next. So here is, I might say, two notions of substantial sets. Substantial in the sense that the density is strictly positive, and substantial in the sense that summation 1 by n diverges. So basically it is saying if a set is substantial, then it has enough elements in some sense to do either of these two things. And when you have a subset which has sort of enough elements, then you expect some structures to arise. Now you expect and I expect is less the point, but more the point is how do you measure structures? What do you call a structure? So one way of saying structure is that the set contains arbitrarily long arithmetic progressions. Arithmetic progressions are very structured. So you want to see if arithmetic progression occur in the set. Next. So this is part of Erdos Turan conjecture. I'm sure many of you have heard of Erdos, but in between I will have comments to make. He was, anyway, in 1936, Erdos and his collaborator Turan conjectured, they wrote a paper called On Some Sequences of Integers, and their conjecture was that every set of integers with positive upper asymptotic density contains a k-term arithmetic progression for every k. So they're claiming for any length of arithmetic progression, somewhere it will occur in the set. Mind you, the catch here is that nobody is talking about the gap length. Number of terms in the arithmetic progression is k, but the gap could be anything. Now, I stated here, Erdos announced a prize of $1,000 for the solution or settling this conjecture. I think some of you may not know, Erdos went around, he was a nomadic person almost. He didn't stay in one place. He moved around all the time, traveling with his suitcase. And he gave problems to everybody he met, sometimes not even mathematicians, and kept to $5 prize, $10 prize for solving that. So young students would try to earn Erdos's dollars by fives and tens, but this problem he has given as much as $1,000 in 1936. So you can see that Erdos, it was far away from. I mean, he was far away from solving it himself, and he did think. Erdos and Turan did think this was a very, very difficult problem, and indeed it was. So can we go to the next slide? So I have here a picture of Paul Erdos and Paul Turan. Just to see this Turan, I have never heard many stories, but Erdos, there are many stories. So he just wanted to show this. Next slide. So from 1936, when he announced, we come to 1953. This is the story. Klaus Roth, he proved the conjecture only for the case k equal to 3. And k equal to 3 means that if you have a set of positive density, then it always contains 3-term arithmetic progressions. And his method was using the hardy little circle method, which has been talked about in this series. And this part of his work was mentioned in he got a Fields Medal in 1958. And this part of his work was mentioned in his Fields Medal citation. So this is my epsilon. I have read this paper, and it is essentially hardy little wood circle method means there is a certain amount of Fourier analysis in it. Then in 1969, Szemeredi proved the result for 4-term APs. Actually, Roth had also proved by then for 4-term APs. And surely this big problem was not going to work, k by k, 3, 4, 5. So anyway, Szemeredi proved the general case in 1975, entirely a combinatorial proof, but not ordinary combinatorial proof. It is really a brilliant work. Szemeredi did collect the $1,000 prize from Erdos, and of course many awards, but it's an extremely difficult proof. And now things become, but it's a very major theorem. Yeah, next slide. Yeah, next. So this is Klaus Roth, who proved it for, I have pictures of Klaus Roth, who proved it in 1958 for 3 terms, and Szemeredi, who proved it for all the general conjecture. Incidentally, Roth got the Fields Medal, Szemeredi got the Abel Prize in 2012. Yeah, next. I made a little error here, but that's because of ignorance. I say there are now 2 other proofs. Actually, there are 3 other proofs. but the last one is based on some hypergraphs and I don't know. Same theorem, there are two other proofs, and these two proofs are completely different domains. So 1977, Furstenberg and Katz-Nelson, they gave a proof using ergodic theory. And then in 2001, Timothy Gowers gave a new proof using Fourier analysis and combinatorics. So I think Timothy Gowers' inspiration was that if Roth proved it by certain methods, which were Fourier analytic, then for three arithmetic progressions of length 3, it seems that in this case, the case of k equal to 4 is a crucial one. Once you have that, then with a lot of bookkeeping, you have the general case. So these are very interesting because the proof of this one major theorem is by combinatorics, by ergodic theory, and a combination of Fourier analysis and combinatorics. Yeah, next. So I have a picture of Furstenberg. He got the Abel Prize this year, but he doesn't look, I mean, this is not how he looks today. This is a photograph probably when he proved his theorem many years ago. And Timothy Gowers, who got the Fields Medal in 1908. This particular theorem was proved after that. He got the Fields Medal for his other work. Yeah. Okay, so that is for the Erdos Turan conjecture 1. It is completely resolved, and it is now no longer a conjecture, but it is called Szemeredi's theorem. The other conjecture that I'm talking about now deals with the other measure of a set being substantial. That is, you have a set A1, A2, etc. of integers such that summation 1 over aj diverges. Then for every k, there are k a's in an arithmetic progression. Same thing with this notion of being substantial. Now, so this is the history as to when exactly this conjecture was pronounced is not well known. But in 1976, it is said somewhere that he wrote somewhere that price for this conjecture was 2,500 for a resolution. And later, in a paper which is called Some of My Favorite Problems and Results, in 1996, as part of a conference on the work of Paul Erdos, he upgraded this price and doubled it, that he offers 5,000 for a proof or disproof of this problem. And he says specifically that neither Szemeredi nor Furstenberg methods are able to settle this, but perhaps the next century will see its resolution. This particular announcement actually was published posthumously because he died in 97. This was published in 97, but by that time Erdos was no more. Yeah, next. So the story doesn't end here. This is a very interesting bit on which I wish to find more details. So Erdos is known to have said that it is not known if there are infinitely many sets of 3 consecutive primes. Once again, the case 3. And then he says, S. Chawla has demonstrated this without the restriction to consecutive primes. That means he is dealing with arithmetic progressions of 3, length 3. But then he says that he was told that Chawla was anticipated by van der Korput. So Chawla's paper is 1944, van der Korput's paper is 1939. And what I find absolutely interesting is that the first paper is 50 pages long and the second paper is 2 pages long. But the second paper is the one that is may not be easy to find. It is in the Proceedings of Lahore Philosophical Society of 1944. But to have a long proof, unless Van der Korput's paper contains other things. And actually, for the proof of this fact, so for the case of the set of primes, which is of density 0, summation 1 by p is infinity, but it's a special case. That was proved, let's say, by 1939 or 1944. Yeah, next. So that was a special case proved for arithmetic progressions of length 3. And in 2004, again, just talking about the sequence of primes, Ben Green and Terence Tao proved that the sequence of prime numbers contains arbitrary long arithmetic progressions. Now, this is actually, let us say, the Erdos Turan conjecture 2, but only for a subset, which is a subset of primes. And their theorem is again considered a very major landmark in the scheme of things, because the Green-Tao theorem very much uses the fact that we are talking about prime numbers, and a set of prime numbers have some unique properties, and their methods, it's called an amazing fusion of methods from analytic number theory and ergodic theory. I think also one should say combinatory. So all the proofs that you have, different proofs of Szemeredi's theorem, techniques from those proofs were used along with some analytic number theory to prove the conjecture 2 in this very special case. Yeah, next. So, Ben Green, Terence Tao. I should say Ben Green is a student, graduate student of, was a graduate student of Timothy Gowers. Okay, go to the next one. And in this context, there is a little bit of excitement right now. On July 7th, that's about less than 3 months ago, two mathematicians, Bloom and Sysak, they have uploaded, at the moment, the papers on Archive, and they have submitted, where they have proved the Erdos Turan conjecture 2 for 3-term arithmetic progressions in the generality, not the particular case of prime. And at the moment, the situation is that people believe that their proof is correct because it seems it should be the right way, but it's under review, probably submitted to the Annals of Mathematics. So the 3-term APs for both conjecture is done, but the general conjecture is open for other primes. Okay, next. Okay, so that was what I call the first part of my talk. The second part is almost arithmetic progressions. So this is like in analysis, near enough. So the definition of this is a set of positive integers is said to get arbitrarily close to arbitrarily long APs if for arbitrarily close for all k and an epsilon greater than 0, all k and every epsilon, there is an arithmetic progression of length k and gap size delta such that this quantity, so this quantity here measures for a point a, small a, in my set, it will measure the distance from a point on the, fix a point on the arithmetic progression. It will measure that distance for a fixed p over all a. So basically this will capture, this number in Firma will capture the element of a that is nearest to p. And then we will take the supremum over all the p belonging to the arithmetic progression. So I tried to draw this diagram by hand. On the top line, there is an arithmetic progression as is required. There exists an arithmetic progression. And let's say it's of size length k, and the gap size I have marked in the figure. And what is being said is that it comes arbitrarily closed if this supremum over P, infimum over etc. is less than epsilon delta. That means now this interval around the points of the arithmetic progression of size 2 epsilon delta, it will contain an element of A. Some remark about this delta. Epsilon you can choose to be small, but there is no control on delta. All these results talk about the existence of an arithmetic progression of length k and whatever its gap size. Its gap size could be very large, in which case epsilon delta occurring on the right-hand side of that inequality would not necessarily be small, because we've already fixed an epsilon. We don't know what delta is. But more importantly, it is a small, the distance is a small proportion of delta. That is what I have drawn. Whatever delta is, where you are trapping elements of the set A is proportionate to delta, at least it is small. So this is what is meant by saying that you have an arithmetic progression, you look at the intervals of size 2 epsilon delta around them, then there will be in those intervals, near enough, that is, points of our set A. So that is the definition of a set getting arbitrarily close to arbitrarily long APs, which I'm saying as that they are almost APs. They're not themselves APs, but near enough. Yeah, the next one. And this is a theorem I'm now going to prove for you. This is by J.M. Frazer. I think this proof is adapted from some major other work he's doing, but it can be. Anyway, theorem says that if I have a subset of integers such that the summation 1 by ak diverges, then A is arbitrarily close to arbitrarily long arithmetic progression. So it is not saying that A contains arithmetic progressions, but it says there are elements of A that are near enough to arithmetic progressions, as in the definition. So to some extent, this is still a result of some interest, because the general Erdos Turan conjecture, the genuine one with arithmetic progression, is still open. One may say that it is solved for k equal to 3 after a while, but the general conjecture is open, and Frazer's result of such approximations is for the general situation, any A. Yeah, next one.
So Professor Madan, there is a question which asks if the arithmetic progression should consist only of integers.
Is there a question?
The question is, okay. If the arithmetic progression should consist only of integers.
Tell me again what the question is.
The question is the arithmetic progression consisting only of integers?
Yes, it is consisting of integers, because we are talking about for all practical purposes, all arithmetic progressions are equal. These are in integers.
Thank you.
Yeah. Okay, because the set itself is in integers. But I should say something at this point, that actually all arithmetic progressions of a certain length k, you can scale them. So if they're lying on rational, you can consider them as integers. And so because, the general thing one would say, every arithmetic progression of length k is the same. But anyway, let's not digress there. So now we are talking about this divergence of the reciprocals of the elements, and we are going to talk about yet another measure of substantial, but this is a upper logarithmic density, where what you do is you take the log of the cardinality, I've written bar here, but cardinality of A intersection m plus 1 and m plus n. I'm not saying from 1 to n, but localizing to wherever this occurs, m to m plus n, you divide it by log n. You're not taking the proportions of these two elements, but the log of the numerator, log occurring in the numerator and denominator. And then you will come to this later. You take the supremum over all m. M, mind you, is the base point of that interval. You first take the supremum along the whole set of integers, and then you take the lim sup as n tends to infinity. And the lemma, first lemma is that if A is a subset such that summation 1 over AK is divergent, then this log density is equal to 1. So one should try to get an intuitive feeling for what it means for the log density to be equal to 1. It'll come somewhere in the proof, so I'll explain that then. The next slide. Okay, so we'll assume the contrary. We will assume that the upper logarithmic density delta log is less than 1. And so we can choose a row which lies between delta log and 1. Then there is an integer capital N. That means I'm now looking at the size of the interval n, such that for all m and for all n larger than this integer, this ratio of log of the cardinality divided by log n is less than equal to rho. This is from the definition. And so if you just multiply by log on both sides, log n, and then exponentiate, you will get that the cardinality of the set of A intersection m plus 1 m plus n is less than n to the power rho. So yeah, next. But once you do have that, this time we are going to do some dyadic counting. So our set A intersection, the dyadic block 2 to the power n, 2 to the power n plus 1, that set we call an. And the cardinality of an, we know from our previous statement, is less than equal to 2 to the power rho n. And now what do we want to prove? We are assume the contrary. So we want to prove that then summation 1 over k, ak would be convergent. To measure this, we'll measure in blocks, the dyadic blocks. Dyadic blocks don't intersect, and so you have, and they completely go. So you take the summation 1 over k in each dyadic block, and then sum over what you get. So this is just a standard undergraduate thing that then this is less than equal to for the second sum, the cardinality of the set, and then the largest one that occurs, that is 2 to the power minus n, and that is less than equal to the sum from some capital N to infinity, 2 to the power rho minus 1 n, but rho is less than 1, so that converges. So we have that divergence implies log density equal to 1. Yeah, can we have the next? Okay, so the heart of the matter in trying to prove this result is actually this lemma too. It's a little complicated, but I've tried to draw some pictures. So this says that if log density for some set is 1, then you have A satisfying the approximation arbitrarily close to arbitrarily long APs. So of course, this is approximate. That will complete our proof because divergence implied log density equal to 1. And this lemma is saying log density equal to 1 is really the thing that makes arithmetic progressions come arbitrarily close. Okay, so this is slightly technical, but not that long. So suppose that doesn't happen. Then there will exist for some epsilon and for some k, things with the inequality will get reversed. So there is some epsilon and some k, so that when you have any arithmetic progression of length k, and gap size is not under our control, gap size delta, then this inequality which defines is going to be reversed. That this infimum over p minus a and then supremum over p belonging to this thing will become greater than delta epsilon. So, okay, so we want to prove, what do we want to prove? So that we actually want to prove that in this situation, delta log will be strictly less than 1. So we may, just for intuition, we write 1 by 2 epsilon to be an integer, because we are going to do some subdivisions and knowing immediately that this is an integer. So what we do is we start with some interval occurring in the definition of the log density, such as m plus 1 to m plus n. Then when I write mod, actually I mean the length of the interval, not the number of points. Number of points in integer points here would be n, but the length of the interval will be n minus 1. Yeah, next page. So we take this interval and subdivide. K mind you is fixed, m is related to epsilon is also fixed. So length of the interval, I'm not even bothered whether it's an integer or not. We divide it into km equal intervals of, k is an integer, m is an integer, and mod j is also an integer. Everybody is integer. So we subdivide into equal intervals of length mod j by km and label them. We're labeling now the intervals from left to right, 1 to km. They are km intervals. Now on this, you look at these intervals, look at their centers, let us say, and form congruence classes modulo n on these labels and intervals. So you've taken an interval of length m and then congruence classes. Then I look at the centers of the intervals lying in the same equivalence class from an arithmetic progression, from the same equivalence class, and observe that they form an arithmetic progression, because you are taking things modulo m of length k and gap size mod j by k. In the next picture, I show exactly what I'm doing. Can you see the next one? Okay, so what we are seeing here is a handmade picture. So it is 0, then there is an m plus 0, 1, 2, m plus 1, etc., then 2m all the way to km. They are being divided into these small intervals. And what I've marked in red are the ones in the same congruence class, because congruence class is modulo m. And then, and there are how many? There are k of them. So k points I have, and I look at these intervals. I look at each congruence class. So I look at all the red intervals, let me put them down. There are k of them, and they form an arithmetic progression. Okay, so that is the subdivision. K of them, and in each congruence class, and that way together they are the whole interval. Next one, please. So now what will happen is that at least one interval from each equivalence class cannot intersect A, because if all of them did, for example, in the red intervals, all of them had a point of A, then the distance P minus A would be less than epsilon delta, and then naturally supremum will also be less than, the infimum is less than delta for each P. Each P in that, that is to say the centers of the intervals. So if that it is going to be there, then it will be less than epsilon delta. But we have assumed that this supremum is greater than epsilon delta. So at least one of those intervals, this inequality has to be reversed. It has to be the situation that at least one of the intervals, the small intervals, cannot contain a point of A. So A intersection J is therefore contained in the union of K minus 1 M intervals. Now that is in each column there is one missing, K minus 1 left, and there are M columns there. So K minus 1 M intervals will be ignored by our set. And the length of each of these intervals is mod J by Km. So what's happening is that in every vertical column there, one interval is getting left out. That means left out by any element of A belonging there. All right, next. So now this is a step we will iterate on each of the remaining and each of the intervals that intersect A. So instead of the interval of full length, we now have these small intervals and we do the same subdivision all over again. And then you keep doing it. Every time you're going to remove one interval at least. So if we do it for n steps of iteration, then we will find that A intersection J is contained in the union of K minus 1 M to the power n. That is, at each stage, instead of Km, I'm getting K minus 1M, and I keep repeating this. And the interval, at each stage, the interval size becomes small, that is 1 over Km to the power n. Okay, so up to what point do we do this subdivision? We do it up to a point n, which is the smallest integer, such that the length of these intervals becomes less than 1. Now at this point, each of these intervals can contain at most one element. Otherwise, there could have been more. And this is the choice of the smallest integer. Here is going to play a role, which of course means that n minus 1, for n minus 1, the inequality will be reversed. Yeah, next one. So finally, I've written a set of inequalities, but we look at them one by one. So the first inequality is, of course, what we start with. The second inequality, our choice of n is such that n minus 1 has a reverse inequality. So what has happened is that K minus, so I'm writing in the first line, I'm writing n as n minus 1 plus 1. So the plus 1 is sitting in the second line, and n minus 1, the inequality got reversed, so it is less than equal to this quantity. So that the choice of n is made such that n minus 1 is less than log n minus 1 divided by log km. That's what's written at the second inequality. And I must say that for a while I got confused, but the third inequality is nothing but to say that n alpha to the log beta is beta to the log alpha is what he's done. To bring in the log k minus 1 and to bring this n to the power rather than k minus 1 to the power. So this is how these inequalities work. The next one, please. Okay, so I'm rewriting that inequality, the final inequality. The cardinality of A intersection m plus 1 m plus n is less than equal to this. So again, what I need to do is to take log on both sides and divide out by log n. And a straightforward algebraic thing then tells you that in the limit, this will just be log k minus 1n divided by km, which is a number, whatever k, but it's less than 1. And k was fixed, m was fixed, so this ratio on the left-hand side to measure the log density will be less than 1. And that proves that log density is less than 1. Okay, that's the theorem I wanted to prove, and I will stop here.
Thank you, Professor Madan, for the very nice talk. We have some questions that I have got from the chat box.
Yeah.
So there was a question which I missed, and I should have asked you during the talk itself. Was that if you allow me to show the slide where it came, can I do that?
Yeah, sure.
Yeah. So the question was about this. So this was not very clear. So what was the converse, and why is it not true?
Why is it?
Why is it not true, the converse? So this was not very clear.
Oh, the previous thing said that if the if dense, so we had a theorem which says if density is positive, then you have divergence, right, of the corresponding reciprocals. This is an example which says that you do have divergence, but the density is zero.
Okay.
So when you have divergence, it doesn't mean that the density is positive.
Okay. Thank you. The next question that I got was, is the proof of Szemeredi for Erdos Turan theorem related to the Szemeredi regularity lemma? If yes, can you just say what it is?
What did you say? Are these proofs what?
So is the proof of Szemeredi related to Szemeredi's regularity lemma? If yes,
Yes, absolutely, very crucially.
so
Szemeredi's regularity lemma is really a major component of that. Absolutely.
yeah, the second part was, if yes, can you say something about what that lemma is?
Which lemma? In the
Szemeredi's
second part of the talk.
no, Szemeredi's regularity lemma. It's the same
No.
question, two parts.
Oh, okay. No. I have to confess that these are big theorems. I don't know that much about them.
Another question that I got was, why is Chawla's proof so short compared to all the rest of the results that you have shown?
I would love to know, but I don't know how to even look at it, because that journal of the Lahore Philosophical Society, I don't know how to get it. And nothing more I could find on the net about it. So, of course, it is true that this is to be taken seriously, because Chawla was a great mathematician with a great lineage. So there must be, and you see, the important thing is that Erdos knew about that proof. See, he's the one who brought it to the notice. So I would love to find out an answer to this question myself.
The last question that I got from the chat was, Roth and Szemeredi, they used completely different methods for their proofs. So are the methods amenable to each other? I think the question means,
No,
can you?
they are sort of pretty different ideas. I mean, I don't know. I think Szemeredi's lemma and also I think the ergodic theory proof, because actually, let me say this about there is a quantitative part to these results, and there is a quantitative estimate. I mean, I should have written it. I can't hand wave it out. But ergodic theory proof did not give that, so it's not as if you can translate from one to the other. No, that's not true. However, in some sense, it is said that Green Tau theorem actually used from each of these theorems. So they made use of the techniques from each of these different proofs. So they are not related, but they probably apply to certain situation. Terence Tau's main theme, as you have seen, order and structure and randomness. So if you separate the randomness, you discover the structure. But no, I don't think, I have not seen anybody relate them in that manner.
I don't have any more questions in the chat that I got, but since there are not many people, so maybe they can just unmute and ask, or have if they have any questions.
Yeah, you have to go via Manjit.
So yeah, I mean, please feel free to unmute and ask, or if you have any quick comments. Okay, I think there are no comments or questions.
Okay.
Thank you
I'm
so
sorry,
much.
this technology sort of beats me. I can't
No,
handle
it's all right. So thank you so much for giving your time
All
and
right.
for this very wonderful
Okay.
talk.